Hello students, welcome to this video. In this video, we shall solve this problem. The problem is show that there are complex numbers satisfying the equation modulus of z minus a plus modulus of z plus a equals 2 into modulus of c if and only if modulus of a is less than or equal to modulus of c for some complex numbers a and c. Further, if this condition is satisfied, then we have to prove the smallest and largest values of modulus of z for all z satisfying this equation. That means for all the solutions of this equation, so we have to collect modulus of z values and you have to find the smallest and largest value of those values. Okay. So first we shall prove this result. We shall prove that there are complex numbers satisfying this equation if and only if provided modulus of a less than or equal to modulus of c. So in the direct part, as it is an if and only if condition, so there are two parts. So in the direct part, so assume that there are complex numbers satisfying the equation modulus of z minus a plus modulus of z plus a equals 2 into modulus of c for some given complex numbers a and c. So now we have assumed that so there are complex numbers satisfying this equation. That means this equation has some solution. So as by our assumption, so there should be some complex numbers. So that means there should be at least one complex number satisfying this equation. So take that as z naught. So let z naught be a complex number such that modulus of z naught minus a plus modulus of z naught plus a should be equal to modulus of c. So this follows by our assumption. As I have assumed there are complex numbers satisfying this equation, there should be at least one, and I have taken that complex number to be z naught. So z naught satisfies this equation. Now we have to prove modulus of a is less than or equal to modulus of c. So to prove that, I'll start with the right hand side of this equation, that is 2 into modulus of c. As I have to relate modulus of c to a, so I'll start with this. Now 2 into modulus of c is equal to modulus of z naught minus a plus modulus of z naught plus a. So on the right hand side, so I have to be left with only a part. So z naught has to vanish. So for that, I'll use the identity modulus of a minus b. We know that modulus of a minus b is less than or equal to modulus of a plus modulus of b. So this will be greater than or equal to modulus of z naught minus a minus z naught plus a. So just I have used this identity. So now this is equal to, so z naught plus z naught minus z naught gets cancelled. So minus a, it is minus 2a, or it is 2 into modulus of a, because modulus of 2 is 2 into modulus of a. So what we got? So that is 2 into modulus of a is less than or equal to 2 into modulus of c, or equivalently modulus of a is less than or equal to modulus of c. We got the result. So that means, so if there are solutions or if there are complex numbers satisfying this equation, then obviously modulus of a will be less than or equal to modulus of c. Now the converse part. Now, conversely, assume modulus of A is less than or equal to modulus of C. Now what we have to show? Now we have to show that there are complex numbers satisfying the equation modulus of Z minus A plus modulus of Z plus A equals 2 into modulus of C. That means we have to search, we have to show the existence of at least one value of Z satisfying this equation under the condition modulus of A is less than or equal to modulus of C. Okay. So as modulus of A is less than or equal to modulus of C, where A and C are arbitrary complex numbers, so there is a possibility that A could be equal to 0. So A could be equal to 0. So if at all A is 0, then so this equation. So we have to find the solution for this equation, that is modulus of Z minus A plus modulus of Z plus A equals 2 into modulus of C. So if A is 0, the left hand side get reduced to modulus of Z plus modulus of Z equals 2 into modulus of C, or 2 into modulus of Z will be equal to 2 into modulus of C. That means Z has to be equal to C. So that means whenever A is equal to 0, so Z equal to C actually satisfies the equation. So if I put Z is equal to C here, then the equation gets satisfied. So then Z is equal to C satisfies the equation modulus of Z minus A plus modulus of Z plus A equals 2 into modulus of C, which is a trivial case. Now assume A is non-zero. Now A is non-zero. Now in this case also we have to show that there is a Z satisfying this equation. That means you have to find a complex number Z such that modulus of Z minus A plus modulus of Z plus A equals 2 into modulus of C. So for that, start with the right hand side, 2 into modulus of C. So now we have to find Z with this condition. So I can write 2 into modulus of C as modulus of C plus modulus of C. C added 2 times. Then, so I need on the right hand side, how I need modulus of Z minus A plus modulus of Z plus A. So I need modulus. So what I'll do is, I'll add and subtract modulus of A. So modulus of C minus modulus of A plus modulus of C plus modulus of A. Okay. Now I need A here, but here I have modulus of A. I have modulus of A. So what I'll do is, I'll multiply and divide by modulus of A. So multiply and divide by modulus of A. Okay. Then, so this will be equal to, so split the denominator, then it will be modulus of A into modulus of C by modulus of A minus 1 plus modulus of A into modulus of C by modulus of A plus 1. Okay, now, so what about this quantity? So as modulus of A is less than or equal to modulus of C, so modulus of C by modulus of A is obviously less than or equal to 1. That means this difference is non-negative. So this value will be equal to its absolute value. So here also, as this is a non-negative value, so this plus 1 will also be non-negative. So its absolute value will be itself. So replace that value by its absolute value. Then what I will get? Then this step is equal to, so modulus of A into, as it is a non-negative quantity, so its absolute value is itself. So I have replaced the value by its absolute value. Similarly, for the second term also. So as it is non-negative, so that value can be replaced by its absolute value. Absolute value. Now we have the form modulus of A into modulus of B. It is modulus of A into B. So it will be modulus of A into modulus of C by modulus of A minus 1 plus A into modulus of C by modulus of A plus 1. Now multiply A inside. So it is modulus of A into modulus of C by modulus of A minus A plus A into modulus of C by modulus of A plus A. So now we can observe that. So we got the form modulus of Z minus A plus Z plus A. So just the trick is here you have to get the terms of the form modulus of Z minus A and modulus of Z plus A. For that I have added and subtracted modulus of A, then multiply and divide by modulus of A, then replacing these terms by their absolute value, then using modulus property, and finally I am getting this. So I can rewrite this as modulus of Z minus A plus modulus of Z plus A, where Z is modulus of C by modulus of A into A. As A is non-zero, modulus of A is obviously positive, so it is a well-defined complex number. For a given pair A and C with this property, so Z is a well-defined complex number which is actually satisfying our equation. So for this value of Z, modulus of Z minus A plus modulus of Z plus A is 2 into modulus of C, right? So which is a solution of the equation modulus of Z minus A plus modulus of Z plus A equals 2 into modulus of C, which proves the converse. That means whenever this condition is satisfied, then only this equation will have solution. So this proves the if and only if condition. Now the further part. So now under this assumption, that means now we have proved modulus of Z minus A plus modulus of Z plus A equals 2 into modulus of C has solutions if and only if modulus of A is less than or equal to modulus of C. Now assume that modulus of A is less than or equal to modulus of C, then this equation will have solutions. That means there are complex numbers satisfying this equation. Now for all those Z satisfying this equation, you have to find the least and the largest value of modulus of Z. We have to find the least and largest value of modulus of Z. Right? So assume modulus of A is less than or equal to modulus of C. Then by this part, so this equation will have solution. Now for all those Z, for all Z with modulus of Z minus A plus modulus of Z plus A equals 2 into modulus of C. We have, so if I consider that, so modulus of Z minus A plus modulus of Z plus A equals modulus of C. So if you use an identity, so it is always greater than or equal to modulus of Z minus A into Z plus A. So it is of the form modulus of A plus B is less than or equal to modulus of A plus modulus of B. So that implies minus A plus A gets cancelled. So it is modulus of 2Z is less than or equal to 2 into modulus of Z, or that is nothing but 2 into modulus of Z, because modulus of 2 is 2 itself, 2 into modulus of z is less than or equal to 2 into modulus of c, or equivalently modulus of z is less than or equal to modulus of c. So what that means, for all z satisfying this equation, modulus of z has to be less than or equal to modulus of c. That means modulus of z cannot exceed the value modulus of c. So that is the largest value of modulus of z is modulus of c, because this has to be less than or equal to, it cannot exceed modulus of c. So the largest value that it can take is modulus of c. Now we found the largest value. Now we have to find the smallest similarly. So for that one, so already we have this. So call this as equation 1. So by 1, we have modulus of z minus a plus modulus of z plus a equals 2 into modulus of c. Now we have to find the minimum or least value of modulus of z. So thus you have to find, or you have to solve for modulus of z. You have to solve for modulus of z. But this equation is not enough to solve for modulus of z independently. So what I'll do is, I'll consider one more equation of the same type. Let modulus of z minus a minus modulus of z plus a be some b. That means for all z satisfying this equation, calculate this value, calculate this difference and take it as b. So for all z satisfying this equation, calculate modulus of z minus a minus modulus of z plus a equals b. So if I consider this equation only for those z values satisfying this equation, then this will be a system of linear equations, having solution, common solution. It will be having common solution. So now what I'll do is call this as equation 2. Now square it and add. So squaring on both sides. So modulus of z minus a plus modulus of z plus a whole square plus modulus of z minus a minus modulus of z plus a whole square will be equal to 2 modulus of z whole square plus b square. So just have squared these two equations and added respectively. So LHS is added to LHS, RHS is added to RHS. Now a plus b whole square plus a minus b whole square. So what it will be? It will be 2 times a square plus b square. That is modulus of z minus a whole square plus modulus of z plus a whole square. So it will be equal to 4 modulus of c square plus b square. Okay. Now modulus of z minus a whole square plus modulus of z plus a whole square. So it is actually 2 times modulus of z whole square plus modulus of a square. So can expand these two. So here minus 2 into ZA bar, here plus 2 into ZA bar will get cancelled. You will be remained with 2 times of this, which is equal to 4 modulus of C whole square plus B square. Now this implies, so multiply 2, so it will be 4 modulus of Z square plus 4 modulus A square is equal to 4 modulus of C square plus B square. or I have to solve for modulus of z. So which implies modulus of z whole square will be 4 modulus of c whole square plus b square divided by 4 minus modulus of a square. So take this term to the right hand side, it will be minus 4 modulus of a square, then divide by 4. So this divided by 4 minus 4 modulus of a square by 4. So 4 gets cancelled, I will be remained with this. Now what actually I need? I need the minimum value for modulus of z. So modulus of z will be minimum if and only if modulus of z square will be minimum. So if this is minimum, if and only if this is minimum value. So now it is enough to find the minimum value for modulus of z square. So modulus of z square is given to be this one. So if the right hand side is the minimum, then modulus of z square will be the minimum. Now see when the right hand side will be the minimum. So for given a and c, so we cannot give desired values for a and c. So a and c will be given initially itself. So we cannot give desired values for a and c. So we do not have the value of a and c in our hand, but b is there. So b is variable. So if I give the minimum value for this b square, then modulus of z square will be the minimum of all these values. So actually, so these are the values of modulus of z square. Among that I need the minimum. So I'll get the minimum when I give the minimum value for b square, because I do not have these values in my hand. So if b square attains the minimum value, then modulus of z square attains the minimum value. Now what could be the minimum value of b square? You know that for any value b, so b square is, so what is b? Actually it is difference of these two real numbers. So for any real number b square is always non-negative. It is greater than or equal to 0. So the minimum value is 0. So if b square is equal to 0, if b square is the minimum value that it can attain. So if b square attains the minimum value, then modulus of z square will attain the minimum value. So what is that? So note that modulus of z attains minimum value if and only if modulus of z square attains minimum value. So if this is the minimum, the least value, then so for all such z, modulus of z square will be the least, right? Then conversely, so it is if and only if. And by this equation, modulus of z square attains minimum value if b square attains the minimum value. So it is if and only if b square is equal to 0. That is, b square should attain minimum value. And for a non-negative value, the minimum value is 0. So modulus of z attains minimum value if and only if b square is equal to 0. And hence, or in that case, in this case, the minimum value of modulus of z is given by, so minimum value is, you have to take the minimum value for b square. So b square is 0. Put b square is equal to 0, then modulus of z square will be modulus of c square minus modulus of a square. Modulus of z square will be modulus of c square minus modulus of a square. as modulus of A is less than or equal to modulus of C. So this is always non-negative. It is non-negative, and square of this number is a non-negative value. So take its positive square root value. Positive square root value. So only consider positive square root, that is modulus of C square minus modulus of A square. Modulus of Z square is this, means modulus of Z will be square root of this, which is a well-defined real number. Well-defined real number. So thus, given any pair of complex numbers A and C, we proved that, so the equation modulus of Z minus A plus modulus of Z plus A equals to modulus of C has equation if and only if modulus of A is less than or equal to modulus of C. And for all those solutions, the largest value of modulus of Z is modulus of C, and the least value of modulus of Z possible is this square root of modulus of C square minus modulus of A square, and which completes the